It saves so much money. What do you want? Yeah, that's what.
All right, guys, page 11. So before we took our test, we started Unit 2, and we talked about how there's a limit definition for a derivative, which really is just a reworking of the slope formula. But then we have that we adapt the two order pairs to be flexible to allow for the distance to decrease. And if we can somehow decrease that distance between 2 points into one single point, then we have not only an approximation of the slope at that point on the curve, but the exact slope. But we saw that really we're not going to use this in terms of finding the derivative anymore. We have a much more efficient way of finding our slope formula for a curved function. But this is still helpful in terms of sometimes AP exam problems are designed where they show you this notation or some variation of this notation and ask you, what does this mean in relation to the graph you see in front of you? And a lot of times, as long as we recognize, oh, this is talking about slope of some curve at a point, then that's really all we need to know in terms of, but we're not going to use this formula to find the derivative on the AP exam. We have a much more efficient way. And that's what we're going to talk about today. It's called power rule. So let me just go through. First is called the constant rule. So constant rule is, we also use power rule for this instance, but I think it's just easier to just visualize it. And the idea is that if I have a function that is a constant, then that constant's derivative is 0. So for example, f of x equals 5. So imagine what that graph looks like. This is a horizontal line. And what is the slope of this line? No matter where I am on this graph, slope is what? 0. So because the slope is constantly 0, we can also say that the derivative of that function is 0. So anytime you see a constant, just know that that slope of that constant is always 0. So it's a little bit of an exception to the rule, but as long as we can visualize a constant as becoming 0, then it doesn't feel like it's taking a lot of effort. So here's power rule. Power rule is mainly for variable raised to an exponent. That exponent does not have to be a integer value, but it just does have to be a rational value. So it has to be like at least a fraction, like 1/4 or 2/3 or 1/3. So if I have a function that is x to the nth power, where n is a constant, a numeric value, rational value, then the derivative or the slope formula of this curved graph is simply bringing the exponent down and then subtracting 1 from the exponent. Okay. So we bring the exponent down as coefficient in front of the variable, and then we subtract 1 from the original exponent value. So just a quick example here, if my function is 3x to the fifth, then my derivative f prime would just be what? Yeah, we bring the 5 down. We see the 3 in front, and we just multiply. So 15x to the fourth. And 15x to the fourth will just describe any slope on this curve. So if I want to find the slope of this curve at 2, I can just plug 2 in, and it'll give me a really large number, and that number will correspond to the steepness of this curve at that particular x value. So over the course of this semester, you're going to see that power rule is going to be the one that you're going to use the most often. Most problems are going to kind of have this this setup relying on power rule. So it's going to be the rule that you're going to be most familiar with. But it's also a rule that comes with conditions, meaning that we got to be careful. There are ways that students can misuse it or use it in a way that is incorrect. So here are 3 things that I think is helpful to make sure that we do ahead of time so that we don't run into potential issues. The first is, if you see radicals converted to rational exponents, this is more of something that's, I think it's more helpful in terms of, we don't have to do this, but I think it's just visually, it's nice to see what number we're dealing with. So for instance, if I have square root of x to the fifth, this is really the same thing as x to the 5 halves. And then once you write it as x to the 5 halves, you can go through power rule, which is what we just talked about, right? We bring the exponent down and we subtract 1 from the exponent. The second is bringing variable to the numerator before applying power rule. So that means if your variable is in the denominator, power rule is not going to work. So for instance, if my function is 1 over x to the fifth, I cannot do this, even though this feels like it feels intuitive where, oh, I'll just do power rule below and I'll make it 1 over 5x to the fourth. So power rule is not going to work if your variable is sitting in the denominator. You have to bring it up to the numerator first. So for instance, if we're dealing with 1 over x to the fifth, we have to make it look like x to the negative 5. That variable needs to sit up top before this rule can work. So this rule is designed for the variable in the numerator, not designed for the variable in the denominator. So once that x to the negative 5 or that negative 5 comes up, then we can make it f prime is equal to negative 5x to the negative 6. Hello. Okay, sure. Their phone in 36. Let me put your backpack in the front. Okay. And then the last helpful step is you want to resolve your parentheses in fractional terms before applying power rule. So for instance, if I had f of x is equal to x to the fifth times 2x squared plus 1, I can't just do power rule and say, oh, that's 5x to the fourth and that's 4x, and I'm done with it. I have to, if possible, I have to get rid of all the parentheses. And then we can go through power rule. But then I think sometimes there are times when we are not able to resolve the parentheses and we're kind of stuck with the form that we're dealt with. If that's the case, then we'll talk about things like chain rule and product rule that we're gonna see in future problems. But for now, if possible, if you're able to expand, then you want to go ahead and expand. But the big idea is that you cannot do power rule when these are connected by multiplication. We have to either resolve it or we have to do something. We have to involve a more involved rule like product rule or chain rule. But right now we're just talking about power rule, so we want to talk about the conditions required for power rule, right? Okay, so be sure that the function is in the appropriate form, that all three conditions are met before we apply power rule. Okay, so here's example 1. Find the derivative of the following. So y equals x to the 7th. And then the notation for derivative, there's a lot of variation. If we start with f of x, then we put f prime. We put that little that exponent comma notation to indicate that we're talking about the derivative function. Same thing here. If we're asked, if we're given y, we can call y prime to indicate we're now referring to the derivative function. So what does x to the 7th become? 7x to the 6. Yeah. So we always subtract 1 from the exponent. So 7x to the 6. So visually, what this means is this 7x to the 6th is going to give us any slope behavior of the original graph. It is doing the job of describing how the slope is changing on the original graph at any single point. Right. Part B requires a little bit of cleanup. It's nice to see that exponent or that rational exponent rather than radical form. So we're going to first rewrite it. So if I rewrite it, I'm not at the derivative level yet. I'm still at the function level. So I'm just going to say g of x equals cube root of x. What's cube root of x? What can we think of that as? X to the 1/3. Okay. So once we see that 1/3, it's visually it's helpful because we know what number to bring down. We know what to subtract 1 from. So now we can say g prime is equal to. Right, so let's go through power rule. What can we do first? What comes down first? 1/3. Okay, so 1/3 comes down. And then what do we do with the exponent? Subtract 1. Now with the fractions, subtracting 1, we do want to match denominator. So -1 is same thing as -3/3 in order to allow the denominators to match. So what's 1/3 minus 3/3? -3/3. Right. So this is the derivative function or the slope formula to describe the curve behavior of the original graph. Now that we're at the derivative, I'm going to ask you to clean up your derivative if possible. And that just means if there's a negative exponent that remains in your derivative, I would ask you to rewrite it with that negative exponent resolved. So this x to the -2/3, another way that we can rewrite this is we can push the x back down to the denominator and force it to show a positive exponent. So we're going to make it 1/3x to the 2/3. So we're basically letting that x share the same denominator space as that 3. This is fine. Some students ask, oh, can I put it into radical form? You can. So if you want to put it in radical form, you'll make it 1/3 and then cube root of x squared. But I'm not going to be picky. I just want the negative exponent to be resolved. So you can leave it in this form. You can leave it in this radical form. You can even rationalize it. But again, I think if you rationalize it, you're just doing additional step that doesn't need to be there. So again, I think it's easiest if you just feel comfortable with radical form in the denominator and don't feel like, oh, I gotta rationalize it. Otherwise, I'll get points taken off. You won't. So yeah, so feel comfortable with the radicals in the denominator or rational exponent, but just resolve your negative exponent at the end. Okay, part C, I want to find the derivative of 4/x to the 5th. Is there any condition that needs to be resolved if we want to do power rules? Yeah, bring that variable to the numerator. So what's a way to rewrite it? Y equals 4 what? X, yeah, 4x to the -5. So this is now our new starting point. before we do our derivative power rule process. So now we can say y prime is equal to, what's the derivative now?
-20.
Right, x to the subtract 1, so -5 becomes -6. And now that you have your derivative, the way I would ask you, the one thing I would ask you to do clean up is resolve negative exponent. So we'll bring that x back down to the denominator and keep the -20 above. Okay, any questions? All right, part D. Now here we have multiple terms, but all these terms there are no parentheses in the way, so we just have to really treat these like individual problems that just happens to be separated by plus or minus. Now, some of these terms are more ready for power rule than others, so I think the best thing to do is rewrite every term until every term is nice and ready for power rule, and then do power rule all at once. I think the danger of just doing power rule for one and cleaning up the other is that it's really hard to go back and know what you did or check your work when every term is at a different level. So even though it just feels it feels just like you're doing additional work and tedious to just rewrite the same term over and over again. I think it's going to be the best for when you want to go back and double check your work. It's easier to follow your work and catch your mistake if you follow the step. So I'm just going to keep rewriting every term until every term is ready for power rule. So my 8x to the 2/3, is this ready for power rule? Yes. So I'm not going to do anything to it. I'm going to wait until every term is at the starting line. Is 5th root of x ready for power rule? Right. We can rewrite it, right, as what? X to the 1/5. Okay. So now that's ready. 2/3 root x. There's two things that need to happen if we want to get this to be ready for power rule. What do we need to do? First off, root x needs to be written as x to the, yeah, so x to the 1/2 to convert it to convert to rationals, and then that x to the 1/2 needs to come up to the top to get it ready for power rule. So I'm going to do two things at once. I'm going to convert that radical to a rational, x to the 1/2, and I'm going to push that x up to the top, so x to the -1/2. And then the 0.875 is ready for power rule, so I'm going to leave it alone. So I'm going to let, so now everything is at the starting line. Everything is ready to go. So now we can do y prime and just apply power rule for each of them. Okay, so first term, power rule, bring down the 2/3. So 8 times 2/3 is 16/3. What's my new exponent? -1/3. Okay, power rule, bring down the exponent. X to the -4/5. Good. Bring down the -1/2, multiply it by the coefficient that's sitting here already. So I get -2/6 or -2/6. X to the, yeah, -2/2. I'm subtracting 1 from the exponent, but I imagine it as -2/2, so I can visualize the common denominator. And what about 0.875? It's a constant. So a constant goes to a 0. I'm going to put a +0 here just to indicate that's what happened, but you can, leave that blank and not have anything there. I just want to show right now that we're not forgetting about this term. We are applying the derivative for that term. So if we clean this up, then whatever this curve looks like, this formula will do the job of finding the steepness of that original function's curve at any point. So my cleanup stage is just resolving any negative exponents, and also, yeah, I mean, that's what I need to do, just resolve negative exponents. So I'm going to push all these x's down to the denominator, and they will all share the same space as these fractional denominators that's already there. So 16 over 3x to the 1/3 minus 1 over 5x to the 4/5 minus, you can leave it as 2/6. I'm just going to reduce if possible. So 1 over 3x to the 3/2. That's it. All right, page 12. Now it's a two-step process. Now it's asking for f prime of 2. So it's asking for the slope of the curve at 2. So let's think of this as one thing first. Let's find f prime of x first. Once we find the slope formula, then we can involve the 2. So before I can find the derivative, something is out of place. So I need to rewrite it. 1 over x squared can be rewritten as what? Yeah, x to the -2. So what's out of place is that denominator variable. If we want to do power rule, the x squared needs to be in a better spot. So power rule is designed for the variable in the numerator, not designed for the variable in the denominator. So it's going to have to come up first, and now we're ready for power rule. So f prime of x is equal to, we go through power rule, bring down the -2, subtract 1 from the exponent, do some cleanup. Now that we have our slope formula, we can find what they're asking for. It wants to know what is the steepness of this curve at x equals 2, and f prime of 2 is going to give us that number, that steepness of that curve at that point. So f prime of 2, we're just going to replace x, 2 in for x. I get -2 over 8, which is -1. So this 1 over x squared, you don't have to know this, but 1 over x squared looks something like this. So negative at 2, which is probably somewhere around here, the graph is exhibiting a very gradual negative slope. So just trying to give you a visualization as to, oh, what does that number mean? It just means on the curve, the graph has a very almost flat, but still negative slope, but barely negative. Okay, example 3. F of x equals cube root of x squared. Write the tangent line to the curve at x equals 1. So, whatever the graph looks like, maybe something like this. It's asking for the equation of the tangent line at x equals 1. So our goal is we want to find the order pair, we want to find the slope, and then we're trying to build the equation of this line that just happens to skim the surface of the curve at x equals 1. So that's our goal. Our goal is to build that tangent line equation through that point. So we need order pair, we need slope, and then we'll put it all together in with point slope form. So let's go ahead and find the order pair first. Maybe that's get that out of the way. So f of 1, we're just going to find the order pair. Anytime we want to find the y value, we're not going to use the derivative. We're going to use the original function. So 1 in for x. So cube root of 1 squared. Cube root of 1 is 1. 1 squared is 1. So my order pair is just 1, 1. before we get to the slope, let's find the derivative. But before we get to the derivative, let's clean up our functions so that we can get term ready for power rule. So I would like to have those radicals to be written in a better form. So x cube root of x squared can be rewritten as x to the 2/3. Yeah. So now we're ready for power rule. Let's get our derivative built before we find the slope. Okay, bring the exponent down. Subtract 1 from the exponent. Do some cleanup. Now we have our slope formula. We have that radical resolved. The negative exponent resolved. So now we can plug 1 into our slope formula, and that should get us our slope value. So f prime of 1 is equal to 2/3 times 1 to the 1/3. The nice thing about 1 is 1 raised to anything is still 1. So I'm just left with 2/3. So the information that's useful to us is our order pair, which is 1, 1, coming from the original function, and then our slope, which is coming from the derivative, which is 2/3. So let's put it all together here. We have our order pair at 1, 1. We have our slope at 2/3. Now we're just building the equation of this tangent line here. So point slope form. There's our tangent line. Great, thank you.
Thank you.
All right, any questions? I want to do example 4. This is probably the most complicated that power rule can look. I think sometimes later on we're going to talk about something called quotient rule, which allows us to find the derivative of a numerator denominator. But I would always encourage us that if we only see a single term in the denominator, that we avoid. Later on, we're going to talk about quotient rule. But if there's only one term below, I think it's cleanest if we just rely on power rule. So we're going to rely on power rule, even though there is that denominator there. So if there's only one term, if only one term in the denominator. Now, if there were more than one term in the denominator, like if it was like 2 root x plus 1, or 1 minus 2 root x, or 3 minus x, then we're having to rely on a more complicated rule. But I'm always going to kind of encourage you towards this. And also, if this shows up on the test or quiz, I'm going to say, do not use quotient rule, or I'm going to ask you to specifically rely on power rule and not quotient rule to get you. Because I think it's more beneficial to us if we can do this using power rule. Right now, this feels complicated because this is one, it's just one function, which is a mess. So my strategy for this is, why don't we split this up into smaller problems? Remember that if I have, for instance, if I had a fraction that's a plus b plus c over d, if there's only one term below, I can always rewrite it as 3 separate fractions: a over d plus b over d plus c over d. And that's our strategy here. If we can split this messy condensed expression into 3 or multiple fractions, then we can just kind of divide and conquer in terms of, okay, every term is its own thing now, every term is independent of each other. If we can just clean up every term on its own, then we can just do power rule for each individual term rather than having to deal with, such a messy connected problem. So, but the cleanup is going to take a little bit longer if we want to get each term ready. So with each numerator, we're going to pair with the denominator, and we're just going to split this into individual fractions. Okay. Any questions so far? So now the advantage now is, these are completely independent problems. If I can just get every term ready for power rule, I don't have to look at one and use that to just make decisions for the other. They're each going to be their independent thing. We don't have to worry about the other terms when we're working on our single term. So, but the cleanup is significant because there's a couple of things that we have to resolve. So one thing is radicals, and second, these variables have to merge. We can't have numerator power rule, denominator power rule, so we have to find a way to merge these x's. So let me do this: x to the fourth over 2x to the 1/2. I'm just doing some cleanup before I merge the variables. So I'm still at the function level because every fraction, even though it's now very small problems, we still have some work to do. So we have to merge these two variables. So the way we merge them is we bring that x up as x to the negative 1/2, and then we add the exponents. Or you can think of it as we're just subtracting these exponents. So 4 minus 1/2, whatever the result is, which is come up to the top. So 4 minus 1/2 is the same thing as 8 over 2 minus 1 over 2, which is 7 over 2. So I have x to the 7 over 2 over 2. 4 minus 1/2. If I'm dividing like bases, I can combine them by subtracting exponents. Okay. Minus 3 over 2, x squared over x to the 1/2, the same thing as merging them by subtracting exponents. 2 minus 1/2, the same thing as 4 over 2 minus 1 over 2, which is 3 over 2. And then plus 4 over 2. And then x to the 1/3 minus x to the 1/2. This one requires a common denominator of 6. So let me put this off to the side. 1/3 minus 1/2 is the same thing as 2/6 minus 3/6. Right? I'm balancing fraction here. 3 times 2 is 6. So I need a 2 above. 2 times 3 is 6. So I need a 3 above. So 2/6 minus 3/6 is negative 1/6. Hey, we're almost there. Every term is ready for power rule, basically. But I want to just show you what I find to be a helpful step, especially if you have these fractional numbers that's still kind of getting in the way. I think looking at a fractional value below your variable sometimes can throw students off. So just want to encourage you to do this. Anytime you see a fractional value in the denominator where it's just a numeric value, you can literally push it, drag it in front of the variable and make it a fractional number rather than a number below. So for instance, x to the 7/2 over 2, there's a 1 hiding in front. I can literally just make it pull out as 1/2. And so that it doesn't feel like a fraction, it just feels like a number that's in front of the variable. I think many students find it to be a lot less stressful seeing that number in front rather than number below. Sometimes we see that number below, we feel like, what are we going to do with that 2? That's throwing me off. You can always drag that number in front. It just feels a little bit more comforting, not having to stare at a fractional number below your variable. Okay, minus, same thing here. That 3/2 can be dragged in front, and it just comes out in front of the variable rather than below the variable. And what can I reduce this to be? 2. So it's a lot of cleanup step. So now we can do power rule. Okay. Now we can find f prime. We've gotten every term up to the starting line. Our exponent is a rational exponent instead of a radical. Our variables are combined. Our variable is brought up to the top. Everything is nice and ready. So now we can find f prime. So now we do power rule. Now everything up to this point is just algebra. This is the one calculus step where we do power rule. So bring the exponent down, bring the 7/2 down. So 7/2 times 1/2 is 7/4. Subtract 1 from the exponent. 7/2 minus 2/2 is 5/2. Bring down the 3/2. 3/2 times 3/2 is 9/4. Subtract 1 from the exponent. 3/2 minus 2/2 is 1/2. Okay. Bring down the negative 1/6. Subtract 1 from the exponent. Negative 1/6 minus 6/6 is negative 7/6. So we have our derivative. We have our slope formula for whatever this curve looks like. The one thing that we need to adjust is just bring that negative back down to resolve that negative exponent. So f prime, gonna keep everything the same. Just going to adjust that final negative exponent. And then you can reduce this 2/6 to be 1/3. It's fine if you leave it as 2/6. I won't take off any points if you don't reduce your fractions, but I think it's possible. I think it's good to practice that reducing. Okay, any questions? So this is the most challenging of all power rule problems because of all the cleanup effort that needs to be applied before you can even get to the calculus. There are other ways to clean this up. Sometimes you can bring this up to the top and distribute, but I like this way. I think this is the cleanest way. This is the way that that I think can help you avoid the most potential algebraic mistakes. Also, just be aware. I want to point these things out because, as I've taught this course over the years, I think one of the benefits of teaching this so many years is I can, see patterns of student mistakes, and the more information I gather, the more I can kind of point out these issues in the hopes that you can avoid it. So one issue is some students stop here and just leave this as the final answer. Anyone know why a student would do that? Just get up to this point and then just not even move past that point. Yeah, it feels like you've done so much work that you're done, right? It's like, oh, I've done 4 steps, right? Like that feels like a lot. That feels like I'm done. But just understand that all these are algebraic steps, and I want you to know, what's algebra and what's calculus, right? So when you're doing splitting up, subtracting exponents, pulling the fraction out in front, you haven't done any calculus. All you've done is you've just done algebraic cleanup. The calculus comes from power rule, where you're bringing the exponent down and subtracting 1 from the exponent. So just make sure you know where you are in the problem. Sometimes students, they lose track of where they are, and they just feel like they've done so much work, and they just leave their answer in this form rather than taking that one final step with power rule. Okay. Another issue is when students are trying to combine the variables, they would divide instead of subtract. So just keep that in mind, that when we're dividing variables, we're having to subtract the exponents in order to get that variable up to the top. Another issue is if there is a coefficient of 2, sometimes students want to just pull that 2 out in front, and they would just pull the 2 and make it 2x to the 6th or 2x to the 4th or 6x to the squared, or they would multiply the 2 instead of understanding that it's really a 2 in the denominator and not a 2 in the numerator. So, all right, example 5. Find f prime of our function. So here's our function, 3x parentheses x plus 1 squared. So this is an instance of where we have to resolve the exponent, the parentheses. If we want to do power rule, we can't have parentheses in the way. Every parentheses had to be resolved. So this x plus 1 squared needs to be resolved, and then the 3x needs to be distributed through. Careful with order of operations. We cannot distribute the 3x through until the x plus 1 squared is resolved. So my first goal is to try to get this cleaned up. So I'm going to think about what can I do with that x plus 1 squared. Careful that we don't just distribute the x and the 1 through. We have to actually FOIL or expand that x plus 1 squared. So I'm going to make that x squared plus 1x plus 1x, which is 2x, plus 1. And all that is still in a set of parentheses because we haven't distributed the 3x through. But we got to resolve the exponent before the fraction, before the parentheses can be distributed through. So now f of x, we're still at the f of x level. Now we can distribute the 3x through, add exponents. X times x squared becomes x cubed. Right, we multiply the coefficients, but we add the exponents. Okay, so 6x squared, because 1 plus 1 is 2, but 3 times 2 is 6. And then 3x times 1 is 3x. Okay, so now we're at the function level. Now we can find the derivative, f prime. Bring the exponent down, 9x squared. These are nice, easy power rule problems. 12x. Oh, here's something that I want to point out. What do you think 3x becomes? Just 3. Okay, so just think about it this way. There's two ways to think about this. One way is to think about, oh, this is a slope, something in slope form, right? Y equals mx plus b. If I have a number in front of that variable x to the first power, my slope is just that number. If you want to do power rule, you can. If I have 3x to the first power, I can do it this way. Bring the 3 down, 3 times 1. And then we subtract 1 from the exponent. 1 minus 1 is 0. And I get 3x to the 0. X to the 0 is the same thing as 1. So that will lead me to the same result, 3. So if you want to do power rule, you can. But I think it's if you can get into that comfort zone of, oh, that's just 3x. And that's just mx plus b. And whatever number is in front of that variable is my slope. All right, next page, page 13. Okay, number 7, this should be easy here, f prime. Every term is ready for power rule. There's no radicals, there's no parentheses, there's no variable in the denominator. Okay, so f prime equals, right, 3x becomes 3. And then what happens to root 2? 0. So I'm going to say plus 0, but you can leave that 0 out. I just want to show you that we did think about that root 2, and we did apply the appropriate rule, but our slope, our derivative is just 3. Okay, number 9. X squared becomes 2x. 3x becomes 3. 4 goes to 0. As while I have this empty space here, I just want to point out conversions from radicals to rationals. And I want to point out a trouble spot that a lot of students experience. Let me start off with something easy here. So square root of x. If I see the square root of x, what's that? X to the what? 1/2, okay. Fifth root of x squared. What is this? X to the 2/5. Okay. Fourth root of x. X to 1/4. Okay, good. Square root of x to the 7th. X to the 7/2. Put a star next to this one. This is the one that students have the most trouble with. Let me point out some mistakes that students make with this one. I think typically we like to read from left to right. So when we see this, I see students feel like, oh, there's a missing something here. So they assume that it's a 1. So they want to say x to the 1/7, which is not correct. Okay. X to the 1/7 would be this. Okay, that's x to the 1/7. So I think this one, for some, these other ones, students don't have much trouble with. They know, oh, 2/5 and 1/4, but or they would say 2/7. They'll realize that it's a 2 there, but they still want to read from left to right. So then they would say x to the 2/7. So just be aware. Anything that's a square root with a number, this is what I feel students have the most trouble with. Not because you don't understand it, just because sometimes we just get into a habit of doing things, and then we're not as careful with this, and this is where trouble starts. So yeah. And if you're having trouble remembering, like, oh wait, where's the 1 go? Where's the 2 go? Think about this one, right? You know what square root of x is, even without thinking about it. You know it's x to the 1/2. And think about where the 1 and 2 is coming from. That 1 is coming from that hidden number to the right, and that 2 is coming from the root, which is coming from the left. So if you can use this to kind of help you realize, oh, the missing number here means 1, missing number here means 2, and you're going from right to left, you can use this to kind of help you, double check your work, especially if you're forgetting, wait, where is that? Is that a 1 or 2? But I think using this to kind of help you know where the numbers are coming from, I think that can be a good way to go back and double check. All right, 11, what's different is they're indicating the variable that you're working with is u. So now instead of x, everything's turned to u. So what's f prime of u here? First term becomes, yep, minus 5, yep. A linear just goes to a constant, and then the 1 goes to a 0. Okay, 13. What's the variable here? Okay, how do you know that's the variable? Is f of s. They're indicating what that variable is. So what do you think the a is? Okay, more specifically, it is a coefficient, but is it a variable? It's a what? The constant. So think of it as some number. It's just some unknown number. It could be a 3, it could be a 6, it could be a 7. F prime of s. That a is going to have to stay, so it becomes what? 3as squared plus, and then go through a power rule, we get 6/2 or 3s. Let me just try one more here with you. 17. P cubed plus 2/5. It feels intimidating with that 5 below, but what can we do so that it doesn't feel like one fraction? Yep, make it t cubed over 5 plus 2/5. And then before we even do power rule, I think this is helpful. Where can we put that 5 so it feels less intimidating with that 5 below the t? 1/5. Make it 1/5 t cubed, and that way it just feels like every other term. It just happens to be some number in front of the variable rather than having to stare at a number below the variable. So now we can find the derivative. And then what happens to 2/5? Goes away, 0. All right, your homework is just to finish up to page 14. So we've done, we started, our homework is really a lot of our classwork. So you can finish up page 13 and 14, and that'll be due tomorrow. Guys, I'm still missing quite a few students. Not signing up for AP registration. So if you can do that sometime today, that'll be great. Otherwise, I'm going to reach out to you individually and see if you can finish that up for me.
Yeah.
Wait. No, sorry, we always put the bill. It's annoying. There we go.
I get it.
Thanks, guys. Have a great day.
Yeah, the setting if you like. Now, only since you left your, access to yours. Yeah, but there's all the repairs.
Thank you. Thanks. Have a good day.
Have a great day. Thanks.
Thank you.
Oh,
I know.
thank you.
Hi, thank you. See you guys tomorrow. I can, I'll write your name down and then, once the nominations come out, then I can nominate you. Okay, I'll put you down. Yeah, sure.
Have a good day.
Have a good day.
Good, how are you?
So you'll come in later today
Yeah,
to
fourth period.
fourth period? That was good, thanks.